We'll now look at some of the different types of angles and some of the theorems that result from them. The first is that of supplementary angles. And the idea of supplementary angles is that the sum of the angles is a straight angle. If I add the measures of these two angles, I get a straight angle. The next is adjacent angles. These are angles with a common side and a disjoint non-empty interiors. So the main thing is they share a side, but their interiors do not overlap. Related to supplementary angles, we have complementary angles. The sum of these angles is a right angle. And then, of course, we need to define a right angle. A right angle is an angle having measure 1/2 that of a straight angle. So it's exactly half of a straight angle. We then have an acute angle, which is an angle with measure less than that of a right angle. And then an obtuse angle, which has a measure greater than a right angle. Now that we've defined lots of different types of angles, let's look at the idea of congruent angles. Congruent angles are angles with the same measure. Two angles that have the same measure. And this is how we denote it. Angle 1, and then this symbol that's an equal sign with a little squiggle on top of it, angle 2. And that symbol is read as congruent. So this says angle 1 is congruent to angle 2. So congruent angles are going to be very important for us. Let's look at one more definition of a type of angle. Our last definition for different angle types is going to be that of vertical angles. The idea, the two angles have the sides of one opposite the sides of the other. So what exactly does that mean? It's essentially that we have two lines. And we're going to look at this angle here and this angle here. These would be vertical angles. If I go ahead and label the rays that make up these angles, we can see the one on the right comes from rays H and K. The one on the left comes from H prime, K prime, the opposite rays. We'll now prove the theorem that vertical angles are congruent. So here's a little bit of a diagram that'll help us visualize what's going on. Let's start by supposing our two angles HK and H prime, K prime are vertical. Since K and K prime are opposite rays, I know that the measure of the angle HK plus the measure of angle HK prime has to be equal to 180. In addition, since H and H prime are opposite rays, I know that the measure of angle H prime, K prime plus the measure of angle HK prime has to be equal to 180. Since they're both equal to 180, I can set them equal to each other. And since these are just numbers, I can subtract the measure of angle HK prime from both sides. That gives me the measure of angle HK is equal to the measure of angle H prime, K prime. And since their angle measures are the same, they must be congruent. Now that we have our vertical angle theorem, we can talk about axiom 10 again. Axiom 10 said that if I have a point D in the interior of angle ABC, then I can say that ray BD is between the two sides of that angle. I now want to look at the converse of that. If I know a betweenness relation, then I can claim a point is in an interior. So this says if the measure of angle ABD plus the measure of angle DBC is equal to the measure of angle ABC, so I have my betweenness relation, then either D is in the interior of angle ABC, or D is an interior point of one of the sides of ABC. So we will prove this one. We'll start by introducing some shorthand. I'm going to let H be the ray BA, K be the ray BC, and U be the ray BD. When the measure of my angle is not 0, and D does not lie on the sides of angle ABC, then we know that HUK holds by definition of the betweenness relation for rays. If my point D is not in the interior of angle HK, then K is not equal to H prime. Because if K is equal to H prime, then this is just a straight angle, and the entire plane is the interior. So it wouldn't make sense. So if D is not in the interior, it can't be a straight angle, so K cannot be equal to H prime. This tells us that either D has to be on H prime, it has to be on the ray K prime, or we have to have one of these three betweenness relations. However, keep in mind that we do know we have the betweenness relation HUC. And while I won't prove it, we can actually get a contradiction on all of these. So since all of these lead to a contradiction, the only thing I assumed in the first place was that D was not in the interior. Therefore, it must be in the interior. And while this isn't a whole proof, it's very much just a sketch and outline of the proof, we do get the general idea of what's going on here.